So now we will prove one, form of a theorem, one theorem, which help us to actually apply Lagrange inequality to some other specific problems in an easier way. So we can directly apply Lagrange, inequality to a specific problem. Then we have to kind of choose the alpha, the vector alpha, the weight vector alpha in a way that help us to, deal with the problems. But by introducing the following concept, we can actually make this choice of alpha in kind of more implicit in a sense. So let's consider again the omega is a product space. And let's say h is a function from omega to r. And let's say this is a K-Lipschitz function if hx and hy differs by most k. Let's write this as a capital K. Whenever x, y differs in almost one coordinate. So this kind of coincides with the previous definition of Lipschitz with, when gradation here is just P1, P2, and P3, and so on. Pi is the first I coordinate. Anyway, so we have this K-Lipschitz condition. And we consider some function and h. And we say that h is f-certifiable if whenever hx is at least s, there exists I, which is an index set, and we can actually bound the number of such indices so that all points y in this omega that agrees with x on the coordinate I have large h value. So what it means is that this h is some parameter that we want to consider, and then we want to show that this is kind of concentrated in the median. And we say that this satisfies this good property, meaning that there are not so many coordinates. That's quite important, determining this value h. Not determining, but taking a lower bound on this. So ensuring this is high, there are a few coordinates which is important. As long as that important coordinates are in certain way, we can actually ensure that, those points with that having that pattern on this coordinate have a large SH value. So for example, if you consider graph, again in a graph model, this random graph gives us the measures on graph. And if you have a graph, and let's say we want to compute the say size of largest size of edge disjoint triangles. Then that's our H. H of G is the largest size of edge disjoint triangles in G. Let's say it was 5 here, and as long as, so this is 5 means that there are 5 triangle edge disjoint, right? And once we have that, as long as we can choose these 15 edges, 15 pairs, as long as these 15 pairs are all edges, then if you take other graph G prime, even if this G prime is other graph, as long as it has these 15 pairs as an edges, just like G, then this also has a H value. Why it's not writing correctly? Its H value is again at least 5. So in that case, this H is fx is 3x. Then H is 3x, f certifiable in this case. So as we have shown just now, it's that this size of largest collection of edge disjoint triangles satisfy this condition, and there are several other graph parameters that satisfy this condition. So if we prove certain theorem which can be applied to all parameter which is f satisfiable, then that's quite convenient for us to apply that theorem to other specific applications. So again, f and h are given. Let's say h is a k-Lipschitz function, which is f certifiable. And let's just say that if this happens, then we say that this coordinate certifies this inequality. And let x be a point, say randomly chosen from omega according to the probability measure, according to the product measure. And let's say x is a random variable, which is h of x. Then for any b and t, what we have is the probability that this random variable x is below b minus t times k square root of fb times probability that x is bigger than b, bigger than or equal to b, is m mod e to the negative t square over 4. Again, by taking b as a number close to median, it shows the concentration around the median. So now we prove this. So let A be collection of points x such that hx is smaller than b minus tk square root of fb. And what we want to show is that the following. We want to show that suppose that y is a point which has h value at least b, then it's actually in A sub t. If we know this, and then we can apply the Lagrange inequality, and then we can actually check that the Lagrange inequality, the left-hand side, is same with this. As H is F certifiable, there exists a set I of indices with size most FB that certifies this inequality. So we take alpha vector whose ith coordinate is 0 if this I does not belong to this capital I, and let's write it this way. And if it belongs to I, then we take this. This is to, you just take the same number for every coordinate in I, and then you normalize it, and you get this. So we want to prove this by contradiction. Wait, sorry. Is it what you want to show? Let me check. Sorry. I didn't write it correctly. We want to claim that this is not in A sub t. Yeah. Then we can actually get the, this from the Lagrange inequality. As a contrary, suppose that y is in A sub t. Then what do we know? Then this low distance between A and y is most t. Then by the definition of this law, there is G in A, so you have y and A. There must be the one which makes this most t. Such that this alpha weighted Hamming distance is most t. So let's write it. I, yi, and gi are different among this I. You sum up this alpha value, then that's most 1. Then what does it mean? Then g actually differs from y in most, from this, what you know is most t times square root of size of I, which is most t times square root of fb, coordinates of I. So let's say y is something like this, and g is, let's say, okay, g is something like so let's say I is here. Then y and g differs on I at most one coordinate, but the rest of them are same. Outside of I, we don't care. It could be arbitrarily different. Then how we wanna do this is let y prime be a new point which agree with y on I and agree with g outside I, meaning that you have the same coordinate outside of I with g, and inside you have the same coordinate with y. Then what do we know? By certification, meaning that this and this are same, then by certification we have h y prime is at least b. But now what do we know? Between g and y prime, they are all same except this one coordinate. So now y prime and g differs in at most t square root of fb coordinates. And so by the Lipschitz condition, we have that hg is at least h of y prime minus t times k square root of fb. So which is at least b t k square root of fb. Give me a moment. Did I write something wrong? What was A? Okay, so we took A to be strict equality. Anyway, so from here, we have this, but then G is not in A, which is a contradiction. Contradiction of our choice of G. So we have this. So meaning that if you take the probability of x being at least b, then that's the probability of complements of a sub t, which is 1 minus probability measure of at. So by Lagrange inequality, what we know is let me check. By taking A, this. So this and the desired inequality is almost same except this one, difference between the inequality, whether it includes inequality or not. But if you see, then this holds for arbitrary t, and this right hand side function is continuous. So we can actually take that give me a moment. How do I explain this? It seems that I have gone over quite a time, so I will maybe briefly explain, how to change. It's not so difficult. Okay, let's just say that because of this function is continuous, and then everything here is, this holds for arbitrary t. So, it's not difficult to actually replace, check that this we can replace with this inequality. So we have this. So I will, so we have this form of theorem, and now in the next time we will use this to get some, we will use this to prove some concentrations on several other problems.